Okay, very good. I'm going to talk about compressive sensing. I'm part of ASML Research. We are a company that's very heavy in software as well as hardware, although most people do know us for hardware, but there's also a complexity of algorithms and software in our company. So if you have had any experience with photography, you could have seen that you can save images that are very huge when they come out of a camera. But you can save them as a JPEG file very effectively into just a few hundred kilobytes. So that's generally a very good thing, says that compression is very successful. But if you want to look at it from the other way, from a sensor design, so the view of hardware, which is also sometimes the ASML view, you see there's kind of a failure of the sensor design. It means that you've done too much of measurement. So can you do better? And here you can see the typical workflow. You measure something, here you sample it, means that you go from analog to digital. Then you have n numbers. So this is this huge file that comes out of, for example, CCD of your DSLR camera. Then you can do compression to go a much smaller size, a few hundred kilobytes, store it, and later reuse it. And decompression is generally not a very difficult task. So what happens in compressive sensing is that now your hardware not only measures, but also compresses. This means that now a compressed number comes out of your hardware. And instead of decompression, you have to do reconstruction, which is a harder task. So you push the complexity from the hardware to the software. And this has a lot of applications inside ASML, but also outside. For example, for outside ASML, you can think of Internet of Things, where you have cheap sensors or sensors that have limitations in their bandwidth, in their energy usage. And what you want to do is essentially having a very low energy hardware, and then push all the complexity on the reconstruction side. Sometimes you want your hardware also to do a basic encoding for security reason, encryption for security reason. And this is not in the scope of this talk, but compressive sensing also does that. So in short, your hardware compresses things, pushes all the complexity to the software side to do reconstruction. I want to give you an example. This is an example that really opened a whole new host of applications for MRI, for magnetic resonance imaging. So essentially for pediatric applications, children are not very cooperative patients. So they would move a lot, that would cause blur. You cannot ask them to hold their breath for 2 minutes. They can maybe do that for 10 to 20 seconds. So shortening the time, here you use compressive sensing to shorten the time. How you do that? MRI measured in the Fourier domain. So measures the Fourier coefficients of that image. And you can see that here I subsample essentially these Fourier coefficients. And the low frequency you subsample, this is a 2D Fourier analysis. And on the for the lower frequencies, you essentially sample very densely, and very sparsely you sample the higher frequencies. And from this subsampled image, you can reconstruct the full MRI image. That's the idea behind compressive sensing. And for that, we actually can sometimes change the hardware as well. There's another example, more abstract. So here, you want to measure this image L. And these numbers that are essentially white, these are the non-zero numbers, and everything else is zero. You have m measurements, so every column is a measurement. And what is a measurement? Is multiplying this image with a random pattern. So this is the result of the multiplication, and summing the number of white values. So here you have 4, you get the measurement, the measured value is 4. So then you have 1, 2, 1, 2. And with these measured values, so you do just the inner product of your image with a random pattern, you can reconstruct this L. So now instead of have a n by n image, you would just have 5 measured values. And your hardware can be designed sometimes to do this step in one easy go. So to multiply with a random pattern. This is the notation I used throughout this talk. M is the number of measurements, K is the number of non-zero elements, and N is the number of pixels. So the problem dimensionality. Another example which may be more familiar for people in data science is in painting. Here, you can say that you have an image and subsampling the image itself and filling up the missing values is a well-known practice called in painting. These days you do it mostly with deep neural networks, but compressive sensing methods were one of the first methods that have been used to solve this problem. So on the summary and outlook, you trade off the number of measurements with higher software complexity and more extensive calculation. This has business impact, so you can have simpler sensors that get the possibility to compete with more complex ones. On the application, you can have a gain between 2-fold to 10-fold in terms of number of measurements or time. There were different applications. MRI, I've shown Internet of Things, so you can have sensors that are limited bandwidth and battery power. And for example, sometimes you can have super resolution. Again, this is an application, you know, in data science, but also in hardware. You can have a limit to your hardware, to your microscope, which we call a Bay or Nyquist limit, and we can go beyond that with these techniques. So what are the pillars of the compressive sensing? The two main components of the compressive sensing are the prior knowledge and the type of measurement that we have, this incoherent measurement. If you remember the L image, that was an example of an incoherent measurement where you measure essentially globally by multiplying your signal with some random pattern and summation. So prior knowledge, I'm going to now explain. So we have signal F here on the lower panel. The signal F happens to have in the Fourier domain a sparse representation. Now Fourier analysis can be thought of as a matrix multiplication. So this is your signal of interest and X is your representation. Again, sometimes you see the word representation in data science with a very complex system, for example, a deep autoencoder, but it can be as simple as a linear model. PCA also gives you a representation. So here X is a Fourier transform, which happens to be 0 most of the time. And now I'm going to sample this signal F in an irregular grid and much lower than what we call the Nyquist rate. So in signal processing, there's a dogma. You have to sample as fast or twice as fast as the highest frequency. And here you actually go below that. You kind of measure less and measure in an irregular grid, which is these red dots here. These are the measurement points of your signal. If now from these, I want to reconstruct my signal and go back to its representation, if I use, this is just a linear system, if I use a least square estimate, I get a lot of noise. But if I use the knowledge of that this signal was sparse in the frequency domain, then I can exactly reconstruct it. So even without noise, you cannot exactly reconstruct it. This is the effect of prior knowledge, what you know about the signal prior. And this is the key enabler of this technology. However, real signals are not sparse. So you need more advanced priors. In reality, for example, this is a wavelet coefficient of a famous image called Barbara. And you can see that this is heavy tail. This means that it has a lot of very large values and it's not spiked here. So there is a lot of mid values as well. We call this power law. They occur most of the time in nature. They are very, very common. And because of this reason, you will see that the sparse assumption is not that successful. And this is where data science comes into play. Modern techniques have been used to come up with very interesting priors. And I'm going to talk about that at the end of the talk. So how about the sensing problem? So this is my hardware, and I want to sense something. Sensing in this talk is also a linear operation. So F is the signal of interest, and Y is what you actually comes out of your hardware as a sense value. So if phi is sinusoid, if you multiply your signal with sinusoids, you're going to get Fourier coefficients. If phi is integrating over a certain area of pixels, you're going to get pixelated images, and you can have super pixels there. So we can think of these as linear transformations. So overall, measurement itself, going from an image to a measured value, is essentially done by a sensing matrix. The signal itself has a representation, which we often assume is sparse. Now I can create a relationship between my measured value, what comes out of my hardware, and my representation. And that is essentially just a linear relation, A equal to phi psi. So again, if I look into, as an example, this was my image, this is Y, and the phi here is this random images. And here A equals to phi because the image itself is sparse. So there is essentially no transformation involved to go to a sparsity. So in a nutshell, you have to just solve linear systems. This system of equations is fat and short. This means that the number of unknowns is much larger than the number of equations, so you don't have enough equations. And to solve that, you need extra assumptions. People used to use a sparsity to do that. Means that most of the elements of X is 0, and there's just only a few non-zero values. But it can also have fancier priors that now we use data science methods to do so. If you do it from a hardware perspective that is generally relevant for my company ASML, you generally see that A is constrained by hardware because it has two components. One is the measurement value, the matrix phi. This is hardware dependent, and psi is more data science algorithm related, is a transformation. Not every A allows you to solve this system. This has to have some properties. And that property means that if you have K sparse signals, so signals that are 0 everywhere, but in K points in their representation, it should keep them separate. If two signals are separate from each other, after A is applied, they have to be separated. And you call that restricted isometry property. And A can be a fully random matrix. So imagine that the first time I saw it was very surprising. You get a signal multiplied by random numbers. And what comes out of that is your measurement. So you need actually measurements that order essentially order number of non-zero elements and only grow linearly with the number of pixels. So if you have millions of pixels, this is logarithm of millions of pixels. It scales very favorably in terms of the space that you're solving. So if you have a statistics background, this basically solves a very high dimensional inference problem very efficiently. If you want a Python example, a very simple case of that is the L1 reconstruction. There is actually in the scikit-learn, there is a case of tomography reconstruction with L1 prior. And that's a case you can try out in Python, and there are much more advanced libraries as well. In ASML, lots of times we do develop our own algorithms because we have very stringent quality criteria, we have very stringent timing criteria, and that has to match with our hardware. But for understanding the method, this is good. So if I want to go to a more formal description of the problem, you want to solve a linear system, and this is actually now, you want to minimize the number of non-zero elements in your representation subject to your measurements are essentially held. So this means that you're solving an L0 norm problem. And this, most of the time, ends up being an NP-hard problem. So if n goes to infinity, the length of this vector x, essentially, you cannot really solve this using standard computation techniques. It looks like finding a needle in a haystack. So it's possible, but not really feasible. Soon it becomes infeasible. the same argument that is often used in cryptography as well. However, there is then a magic called L1 magic. This is essentially what really started this field and put this name around 2006. And this is if you have enough measurement, which means that your number of measurement grows with the number of non-zero elements, as well as the log of the space that you're solving, so the total number of pixels, we can solve this very difficult prior with a much simpler prior. So you have to solve this L1 problem subject to your linear constraints that are coming from measurement. And this is also finding a needle in the haystack, it's just the needle is much bigger. So now you have a convex problem, and these problems can be solved in polynomial time. And there are very powerful tools for it, and there's lots of proofs of convergence and very, very beautiful theory. So this really started the field. Now, an overview again. If I have m measurements of some object that has k non-zero elements, if m is less than k, I essentially cannot solve that problem. This is impossible in the information theoretic sense because I have insufficient information. And this is like finding the black cat in the dark room. We as humans are very good at it, finding patterns that they don't exist. And this is gets slightly better if your number of measurements, your m, increases after a certain point. So if m equals k, now you can solve this. It's very hard to do that. So it is computationally infeasible. You can solve it in a smaller scale. In a larger scale, you can't solve it. If this is just too much hay, then you cannot find this needle. And then if you further increase the number of measurements, then this becomes a simple problem, right? And this might be trivial, but it has a very interesting connection to physics, actually. This is a 2D diagram called the phase diagram. K divided by n is the probability of non-zero value. So here, every element of your representation has a non-zero value, and here everything is zero. Here, m divided by n is measurement rate. And 1 means that every pixel is actually measured, or the number of measurements equals, for example, the number of pixels. And here, you basically made no measurement. So this is the region where you can't solve. You don't have enough measurements. This is the region that you can solve, but for different classes of signals. And now I just talked about the sparse signals, so this blue curve. Between these two regions, there is this gap that L1 norm doesn't work. So inference is infeasible. And after that, you get another phase transition, which allows you to do inference. These are, by the way, asymptotic results that come from some statistical physics theory and a method called replica method. And yeah, there's a very beautiful relationship between these phases of matter. So here we have this inference problem that is impossible, hard, and easy. And suppose the matter wants to go to the crystal state. So in the liquid state, that just doesn't happen. There is a point that it can happen. The matter can go to crystal state, but maybe it gets stuck in a state, the local minima of what we call free energy. You can see free energy and all over also the machine learning literature, for example, in autoencoders, variational autoencoders. And then there is a point where it's easy to find that crystal state. It's the same happening here. And this is not a pure analogy. The mathematics of it is the same. So the mathematics that governs inference and data science is the same, the mathematics that governs the state of the matter. Going back to the fact that signals are not sparse, here again is the measurement, the probability of getting a non-zero value over some data set. And this is a histogram of the amount of non-sparsity. So if you're here, you're very sparse. And if you're here, you're really not sparse at all. And so you see that a lot of images have a large degree of more than, say, 30% or so non-sparsity. So natural signals are not really sparse. And if I now mix this with these results of the phase transition, that how much data you need such that things work. If you're in this region, say, around 20% on sparsity, your measurement rate can just be half. So essentially, you can measure half the number of pixels such that things work without any error, which doesn't look that good, actually. So this is where data science really comes and brings value. So suppose this is MNIST numbers. This is L1 reconstruction, so using only sparsity. And you see that with 25 measurements, L1 reconstruction fails. So it's in the region that there is not enough information. If you use neural networks, such as variation autoencoder or uncertainty autoencoder, you get much better results. And uncertainty autoencoder is actually better than variation autoencoder for this task because it's developed for the compressive sensing method. And essentially, it's an autoencoder where the encoder is a linear system, and the decoder is nonlinear, and the encoder is using information theoretic arguments about essentially what is the best direction to measure such that the posterior uncertainty is minimized. This is a zoo of method, actually, just up to 2017. So with data science standards, this is ancient times. I apologize for that, but that's not the point of this spectrum. What you see in this spectrum is on one end of the spectrum, you see data efficient methods. These are interpretable. They model physics, some sort of. So there's simple models. There is a whole lot of them developed in the beginning. And then there are more advanced handmade priors. And here you see models that are essentially use deep learning. They need a lot of data. They have low bias. They're very flexible. But they don't consider that you're actually solving a compressive sensing problem per se. So really, you don't use the whole knowledge. And the beauty is in between, where you go from a marriage of physics-based models and data science-based models to models that are mixing these two. So this is a whole set of different, essentially, methods. And now I just basically said what is the strategy that these methods use. So these methods treat the problem as a black box, like a feed-forward neural network that does some reconstruction. Here you have based on sparsity, then you have hand design priors. And these are, for example, you take a solver, and this solver is now built to solve, for example, this L1 norm optimization problem, and you unroll it, means that you kind of, for example, if you have 10 steps of the solver, you create a 10-layer neural network, and what each layer does is not a standard feed-forward operation, but something that uses the equations of essentially a solver for L1 norm minimization. Then sometimes you model the priors or the posteriors with essentially a neural network. So these are the hybrid methods. They have a lot of value because they get the best of both worlds. There is some interpretability in them by design, and they also can take advantage of the data, and then they can get much better gains. This is an example of learned damp, AMP. Essentially, it's called approximate message passing. This is an algorithm that works on graphs, and people use that, Montanari actually, to essentially build solvers for this L1 norm problem and prove a whole lot of very nice theoretical results. And what happens is that these operators that generally happen in this solver, you replace them with neural networks. So you keep the equations of AMP. If you know about belief propagation, by the way, AMP is belief propagation on asteroids. So this is, use these equations of AMP and you just replace some steps with a neural network that you're going to train. And these are these hybrid methods. So what happens here is that deep learning is much faster, more accurate. The problem is that it doesn't come with really with guarantees. So this sometimes is a problem. depending on your application and requirements of your customer. If it breaks, how you want to service it, for example. But if I now look into different methods, and these are very powerful methods, these two methods are based on deep learning, and you see here different measurement rates. So here is a much higher measurement rates. You have the number of measurements is a quarter of the number of signals, and here you have just 10% of the total number of pixels you have measurements. You see that your peak SNR is here much better in the case of the deep learning, and your reconstruction time also is faster because this neural network, once trained, can work much faster. And this is very important because we also sometimes have timing constraints. This is actually the talk. I hope I was well in time, and if there is any questions, I would be happy to take it.
Thank you, Iman. This was a really informative presentation. Like, I really like the slides, and I think we already have a first question. Oh yeah, it's about like, are you going to share the slides? It's a great material.
Yes, the slides will be public. Yes,
okay,
we will share these slides.
Awesome. So just to give context to you and everyone, that we have Slack channels, like Slack channel for workshops and everything. So there's a Slack channel called Talks where you can share your resources and ask your questions to the speaker. And I think we have like a couple of minutes, 2 questions for taking questions. So if anyone has any questions, please feel free to drop them in chat or in the Q&A section. Okay, yeah. So just to give attention to everyone, that ASML is hiring across different roles. So if you go on the website and check out the job boards, they have listed I think a bunch of roles which basically intersect with data science and physics, and which is kind of interesting and which is kind of different from all the other job roles that we have on our job board. So yeah, feel free to check them out and apply, or maybe you can reach out to Iman during the conference if you have any questions.
Yes, please reach out. I will write down my the ASML email, then you can contact me. We have a lot of interesting jobs at ASML for this particular application and many other applications related to data science. There are many data science teams in our company. You may not have heard of it, but this is if you use a high-end phone, or actually even mid-end phone, everything, you are using our products that are building the chips in these systems. So we would be very happy to have you in our company. Thank you.
Yeah, Iman. So we have a question from Simona. They're asking, could you please give an intuition of what an uncertainty autoencoder is? It is something for uncertainty autoencoder is.
Yeah, so the UAE. Yes. So UAE is very much similar to VAE. But the linear, the encoding is linear, and the cost function is designed such that so suppose you have an object, and for example, take about PCA. PCA tries to find directions where the energy is maximally spread. So the variance is maximally spread. These are the eigenvectors of your covariance matrix. That's PCA. But those directions are good only, for example, if your distribution is mostly like a Gaussian. If you have 2 Gaussians that are orthogonal to each other, then the direction can be very, very poor. Then you want to have directions that capture each mode separately. In that sense, it would find those directions. It wouldn't necessarily go for directions where data is most spread. It goes for a direction that's maximally informative. And for informativeness, we look into the probability, what we learn about the X given the measurement Y. So it tries to maximize the information of that.
Awesome, thank you. I think that answers the question. So there's another question by Curatinus J. I'm sorry if I mispronounce your name. The question goes like, how do you compare with conventional method like stacking to reduce noise?
I'm not sure if I know what he refers to by stacking actually.
I could give permission to the question to the panel to the attendee if they can ask the question. Let me just do that.
Hi, can you hear me?
Yes, I can hear you better now. Yes.
Yeah. So in the past, we tried to get more data from measurements and actually taking a lot more measurements and stacking them in, like putting them in the same domains, like time domain again and again. And with the hope of we getting more data signal rather than the noise.
Yes.
Like try to improve the signal to noise ratio. It's similar like with taking photographies.
Yes.
Night
Okay,
photographies.
now I understand. Yes.
Yeah, that's what we call stacking. But we don't have. Yeah, but this one you put a lot of more with the computing in deep learnings to do extra work prior to that. So how do you compare to non-deep learning?
Very good question. Yes. Do we have time to answer this now? Indeed, the classical compressive sensing has some robustness considerations with respect to noise. But if you look at it very abstract, essentially, compressive sensing is nothing but trading off one parameter with the other. For example, you can make more measurements, trade some temporal resolution, so you take more time to take more measurements and gain a spatial resolution, for example, better noising. That's what you call stacking. So even you can think of it also as in this class of mathematical models. Or you can go the other way. So depending on your application, you may want to trade some spatial resolution or noise and improve on your timing, or the other way around. Pay in terms of time, measure more, and improve on your spatial resolution or noise performance. Essentially, compressive sensing just allows exactly for this type of trade-offs. But what most people talk in industry about compressive sensing, so the answer I gave you is from a mathematical perspective, they generally mostly refer to the fact that you can save, for example, some time, because, for example, MRI time is the most important thing, while maintaining a reasonable SNR. And you can see that with deep learning priors, then the prior take care also of part of the denoising, because you know where is your data manifold. So you just need to have enough information to point to the correct point on the manifold. Yeah. Is it answering your question?
Yes. So I see the function of the prior. Okay, thanks.
Yeah.
Awesome. Thank you.
Yeah.
So seems like we are almost at the time. We are just at the time, and yeah, I would like to thank Iman for coming today and giving this awesome talk. And you can find Iman on the Slack. You can just search his name in the directory, and I'm sure Iman, you would be on the Slack to answer all the questions that everyone has. And you could also share your slides on Talks channel. It's hashtag Talks. You can just upload the slides over there. So thank you, Iman. And yeah.
Thank you, everyone.